Function of sleepers. Railroad sleeper, also known as railroad tie, railway sleeper, rail sleeper, is one kind of rail fasteners. According to the materials, railroad sleeper can be divided into concrete sleeper, wooden sleeper, plastic sleeper, composite sleeper, steel sleeper. The railroad sleeper has simple structure, but plays vital roles in the railway fastening system. Railroad sleepers support the rail tracks, also maintain the position of rail track, and transfer the pressure from steel rail to rail bed. All types of railroad sleeper should have flexibility and elasticity. When the train wheel on the railroad sleeper, it can buffer pressure and back to original shape quickly. Functions of sleepers are as under: to transmit the load to the formation below ballast, to hold the rails at the correct specified distance, to enable the rails to be seated at a cant of 1 in 20 either directly or over a bearing plate in case of wooden sleepers, to maintain the desired cross level between the two rails in the track with the help of ballast, to provide lateral and longitudinal resistance to the track with the help of ballast, to provide torsion resistance to the track frame with the help of rail sleeper fastenings, to absorb the vibrations set up by the moving loads. Requirements of an ideal sleeper should be able to perform all the functions as indicated above. Assembly, installation, removal and renewal should be possible with ease. Should permit adjustment of gauge. Should have sufficient bearing area to avoid crushing of ballast. Packing should be possible with ease. Handling should be easy. Should have insulating properties for use in track circuited areas. Lastly, above all, should be economical and durable. Density and spacing of sleepers. Number of spacing of sleepers in the track is indirectly described as sleeper density. The sleeper density is designated in two forms: number of sleepers per rail of standard length, or number of sleepers per kilometer. Sleeper density in the form of number of sleepers per rail of standard length is defined as m plus k, where m is the length of the rail in meters and k is a constant varying from 2 to 9 depending on the importance of the line. From the number of sleepers as defined above, sleeper density can also be designated as number of sleepers per kilometer. For a standard rail length of 13 m on BGA, sleeper density of m plus 4 would mean 17 sleepers per rail at 13 meters length or 1308 sleepers per kilometer. Depending upon the density of the sleepers, the number of sleepers in a rail length is decided and their spacing is kept as uniform as possible except at and near the joint. The sleepers on either side of the joint are spaced as close as possible, duly taking into account the space required between two sleepers for packing and also making the joint to behave as suspended joint and not as a supported joint. The next two sleepers, called shoulder sleepers, are so spaced as to maintain a uniform spacing of intermediate sleepers. Standard spacing for joint and shoulder sleepers. Gauge type of sleeper. Note: for long welded rails, a uniform spacing of 65 centimeters and 60 centimeters are adopted for sleeper density of 1540 per kilometer and 1660 kilometers respectively. For short welded rails, sleeper spacing are arrived at based on the above principles, taking into consideration the increase or decrease of the length of short welded rails paved depended upon the system of welding, i.e. thermit or flash butt. Wooden sleepers, also known as crosties or railroad ties, have been widely used in railway track construction for many years. They offer several advantages as well as some drawbacks, making them a subject of interest in the railway industry. Starting with their advantages, one of the most significant benefits of wooden sleepers is the ease of manufacturing. Wood is a readily available and renewable resource, making the production of wooden sleepers cost-effective and environmentally friendly. Additionally, wooden sleepers provide resilience, meaning they can absorb and dissipate vibrations caused by passing trains. This ability to flex under load helps reduce stress on the tracks and other components, contributing to a smoother and more comfortable ride for passengers. Another advantage of wooden sleepers is their ability to distribute loads uniformly. This characteristic is essential for maintaining track stability and preventing excessive wear on the rails. The uniform load distribution also extends the lifespan of both the sleepers and the tracks, leading to cost savings over time. Handling wooden sleepers is relatively easy due to their lighter weight compared to some alternative materials like concrete. This ease of handling simplifies installation and replacement processes, reducing labor requirements and associated costs. Wooden sleepers also demonstrate a certain level of resilience to accidents. In the event of a minor collision or impact, wooden sleepers are less prone to damage than their concrete counterparts. This factor contributes to a more reliable and lower maintenance track infrastructure. Moreover, wooden sleepers are particularly well suited for track circuits, which are used in signaling systems to detect the presence of trains. The insulating properties of wood make it an ideal material for ensuring proper track circuit operation. Additionally, wooden sleepers allow for closer spacing at track joints, which further enhances track stability and reduces the potential for track deformations or misalignments. Furthermore, wooden sleepers are compatible with measured shovel packing, MSP, and mechanized maintenance practices. These methods facilitate efficient and precise track maintenance, making it easier to maintain the desired track parameters. Wooden sleepers, despite their advantages, come with several notable disadvantages that have made them less favorable in modern railway track construction. Firstly, one significant drawback is the declining availability of suitable timber and the subsequent increase in cost. As demand for wood rises and concerns over deforestation mount, obtaining quality wooden sleepers has become more challenging and expensive. This escalating cost presents financial challenges to railway companies and encourages exploration of alternative materials. Secondly, the lifespan of wooden sleepers is relatively short, typically lasting only between 10 to 15 years for durable hardwood variants. This limited lifespan necessitates frequent replacements, adding to maintenance costs and causing disruptions in train services during replacement activities. Another concerning drawback of wooden sleepers is their susceptibility to catching fire. In the event of accidents or incidents involving sparks or flames, wooden sleepers can ignite, potentially leading to significant safety hazards and service interruptions. Furthermore, wooden sleepers are vulnerable to decay caused by attacks from vermin and fungi. The natural composition of wood attracts insects and organisms that can gradually degrade the sleepers, compromising their structural integrity and necessitating earlier replacements. Lastly, wooden sleepers have a very low scrap value. When they reach the end of their usable life, the resale or recycling value of old wooden sleepers is minimal, further contributing to the overall cost burden of their frequent replacement. Given these disadvantages, many railway networks have sought alternatives to wooden sleepers that offer greater durability, longer lifespans, and reduced environmental impact. Concrete, steel, and composite materials have emerged as viable options, as they often provide improved longevity and require less maintenance in the long run. Wooden sleepers can be classified into two categories: treated, T, and untreated, U. The classification is based on whether the sleepers undergo treatment to enhance their service life. The treatment of wooden sleepers becomes imperative for species that are naturally non-durable, such as deodar, sheer, fir, and several others. These timber species possess inherent weaknesses that render them susceptible to decay, fungal attacks, insect infestations, and other environmental factors. Left untreated, these non-durable species would rapidly deteriorate when exposed to the harsh conditions experienced in railway track environments. The treatment process typically involves applying preservatives to the wooden sleepers. These preservatives penetrate the wood, providing protection against fungal growth, termites, and other destructive organisms. The treatment not only enhances the durability of the sleepers but also significantly extends their service life, making them more suitable for the demanding and continuous load-bearing role they play in railway tracks. In contrast, some species, like teak, sal, rosewood, anjon, and others, are naturally durable and possess inherent resistance to decay and pests. As a result, these naturally durable species do not require any additional treatment. Their inherent properties make them well suited for use in railway track construction without the need for chemical treatments. Not only does this save on treatment costs, but it also ensures that the timber retains its natural characteristics and environmental sustainability. The careful selection of timber species and appropriate treatment processes are essential considerations in the design and maintenance of railway tracks. By using treated sleepers for non-durable species and leaving naturally durable species untreated, railway authorities can strike a balance between economic efficiency and environmental responsibility. Moreover, these measures help ensure the safety and long-term performance of the railway infrastructure, enabling it to withstand the rigorous demands of heavy train traffic and varying weather conditions. Regular inspections and maintenance, in combination with the right choice of materials, form a comprehensive approach to sustainably managing wooden sleepers in railway track maintenance. The service life of wooden sleepers varies depending on factors like the type of timber used and the density of railway traffic. To ensure both safety and cost effectiveness, it is imperative that wooden sleepers older than 5 years, currently in use on the tracks, undergo thorough inspections every year. Regular inspections help detect any signs of decay, damage, or structural weaknesses, allowing for timely replacements or repairs, thus preventing potential accidents and ensuring the track's reliability. In practice, experiences have shown that naturally durable wooden sleepers typically have a service life ranging from 10 to 15 years. However, it's essential to remember that this duration can be influenced by various factors, including the environmental conditions, maintenance practices, and the intensity of train traffic. Proper maintenance and timely replacement of worn-out sleepers are critical to ensuring the overall safety and efficiency of the railway network. End binding of sleepers is a crucial practice aimed at safeguarding the inner untreated portion of the sleepers from potential attacks by insects and fungi resulting from shattering and splitting while in the track. It is particularly important for ensuring the longevity and structural integrity of both new and reconditioned sleepers, especially those falling under the T category that require treatment. The end binding process involves the application of wire or hoop iron clips around the ends of the sleepers. By securely fastening the ends, this technique helps prevent the splitting or splintering of the wooden sleepers, which commonly occurs due to the constant stress and pressure they endure while supporting the weight of trains and bearing the impact of continuous train movements. For the T category of sleepers, it is recommended to carry out the end binding procedure before the treatment process. By doing so, the untreated wood at the ends is shielded from external factors that could accelerate its degradation, ensuring that the treated portion remains protected and fully functional throughout its service life. The choice of materials, such as wire or hoop iron clips, ensures that the end binding is both sturdy and effective in maintaining the integrity of the sleepers. These binding elements securely hold the ends together, reducing the risk of cracks and fissures that could expose the inner, untreated part of the sleeper to moisture, pests, and fungi. End binding is a fundamental part of comprehensive track maintenance practices, and its implementation is essential to prolonging the life of wooden sleepers, especially in regions with challenging environmental conditions that might expedite the deterioration process. By adopting this protective measure, railway authorities can enhance the durability and safety of their track infrastructure, minimizing the need for premature replacements and reducing overall maintenance costs. Regular inspections should also be conducted to monitor the condition of the end bindings and address any issues promptly to maintain track performance and safety. final stage of railway track construction involves reprocessing the gravel base to secure the sleepers in place. This crucial step ensures that the sleepers remain firmly fixed, preventing any unintended movement that could compromise the overall track stability and safety. Reprocessing the gravel base serves several vital purposes. Enhanced stability. By firmly anchoring the sleepers into the gravel base, the track becomes more stable, reducing the risk of track misalignment, especially under the weight and force of passing trains. Load distribution. The secure fixing of sleepers evenly distributes the load exerted by trains, minimizing stress on individual components and promoting uniform wear across the track. Noise reduction. A well-secured track reduces the generation of noise and vibrations during train operations, leading to a quieter and more comfortable travel experience for passengers and neighboring communities. Drainage improvement. Properly reprocessed gravel base aids in maintaining effective drainage, preventing waterlogging and preserving the track's integrity, even during heavy rainfall. Protecting sleepers and structures. By ensuring the stability of sleepers, the reprocessing of the gravel base helps protect both the sleepers and other railway structures from premature wear, damage, and potential accidents. The combination of a securely fixed track with a well-maintained gravel base contributes to the longevity and reliability of the railway infrastructure. Regular inspections and maintenance of the track and gravel base are essential to identify any issues promptly and address them before they escalate into more significant problems. By focusing on both the safety of the sleepers and the overall railway structures, railway authorities can maintain a sustainable and efficient track network. Reprocessing the gravel base not only ensures the smooth and safe operation of trains, but also minimizes maintenance costs and extends the lifespan of the railway track, benefiting both the railway operators and the passengers they serve. Comparing wooden sleepers with concrete sleepers provides insights into the advantages and disadvantages of each type, helping railway operators make informed decisions based on their specific needs and priorities. Durability. Concrete sleepers are generally more durable and have a longer service life compared to wooden sleepers. They are resistant to decay, insects, and weathering, making them well suited for heavy traffic and challenging environmental conditions. Wooden sleepers, although treated, still have a limited lifespan and require more frequent replacements. Maintenance. Concrete sleepers require less maintenance compared to wooden sleepers. Once installed, they generally do not need additional treatments, unlike wooden sleepers, which necessitate regular inspections and retreatment to ensure continued durability. Track stability. Both concrete and wooden sleepers offer good track stability, but concrete sleepers often provide better alignment and geometry retention over time. This characteristic contributes to smoother train operations and reduced track maintenance. Cost. Initially, concrete sleepers may have a higher upfront cost than wooden sleepers, but their extended lifespan and lower maintenance requirements can lead to cost savings in the long run. Environmental impact. Wooden sleepers, if sourced sustainably and treated properly, can be environmentally friendly. However, concrete production has a higher environmental impact due to its resource-intensive manufacturing process and carbon emissions. Installation. Concrete sleepers are heavier and require specialized equipment for installation, while wooden sleepers are lighter and more manageable during installation and replacement. Noise and vibration. Concrete sleepers tend to reduce noise and vibration levels better than wooden sleepers, providing a quieter and more comfortable train ride for passengers. Recycling. At the end of their life cycle, concrete sleepers can be crushed and recycled for use in other construction projects, while wooden sleepers have limited recycling options and often end up as low-value scrap. Suitability for high-speed trains. Concrete sleepers are preferred for high-speed rail networks due to their superior stability and durability, whereas wooden sleepers may not be suitable for high-speed applications. In conclusion, concrete sleepers offer greater durability, lower maintenance requirements, and better track stability compared to wooden sleepers. However, wooden sleepers can still be a viable and environmentally friendly option when sourced responsibly and treated correctly. The choice between wooden and concrete sleepers depends on factors such as the specific railway network's needs, budget constraints, environmental considerations, and the intended usage of the track. The construction and installation of wooden sleepers differ from concrete sleepers in various aspects. Wooden sleepers have been traditionally used in railway track construction, and their process of construction and installation involves distinct steps. Timber selection. The first step in the production of wooden sleepers is selecting suitable timber. Different types of wood are chosen based on their durability, strength, and resistance to decay. Commonly used timber species include oak, pine, beech, and eucalyptus. Timber treatment. In many cases, especially for non-durable timber species, wooden sleepers undergo a treatment process to enhance their resistance to decay, insect attacks, and weathering. Various preservatives are applied to the sleepers to extend their service life and improve durability. Sleeper manufacturing. After timber selection and treatment, the wooden sleepers are manufactured in specialized facilities. The sleepers are cut to the required dimensions and shaped to fit the desired specifications for the particular railway network. Transportation to the construction site. The wooden sleepers are transported to the construction site using trucks or railway wagons. The handling of wooden sleepers is generally easier than concrete sleepers due to their lighter weight. Track preparation. Similar to the installation of concrete sleepers, the track alignment and formation are prepared before laying wooden sleepers. The ballast bed is leveled and compacted to provide a stable base. Sleeper installation. Wooden sleepers are manually placed on the ballast bed at the specified intervals. This process involves lifting and aligning the sleepers accurately along the track. Fastening. The rails are fastened to the wooden sleepers using various methods, such as spike fastenings or screw fastenings. Spike fastenings involve driving spikes through holes in the sleeper into the ballast, securing the rails in place. Ballast tamping. After the sleepers are installed, the ballast is tamped using specialized equipment to provide a stable and well-supported track structure. Regular maintenance. Just like with concrete sleepers, regular maintenance of wooden sleepers is essential for ensuring track integrity and safety. Wooden sleepers may require more frequent inspections and retreatment compared to concrete sleepers due to their susceptibility to decay and environmental factors. Comparing wooden sleepers to concrete sleepers, wooden sleepers generally have a shorter service life and higher maintenance requirements due to their vulnerability to decay and insect attacks. However, they offer certain advantages, such as being environmentally friendly if sourced responsibly and treated properly. Additionally, wooden sleepers are often lighter and easier to handle during installation and replacement. The choice between wooden and concrete sleepers depends on various factors, including the specific railway network's requirements, budget constraints, environmental considerations, and the track's intended usage.